Okay, so we talk about equation of equilibrium and constitutive equation. Constitutive equation is also called stress-strain relationship. Okay, so we talk about two set of equation, and they are not good enough to solve the equation itself. So we need the last set of equation, which is called kinematic equation, or sometimes called strain displacement relation. Okay. Strain displacement relationship. So if you remember in solid mechanics 1 or strength of material you have taken, and this initial length is going to be L0, and after applying the load, this extended to this much. So this length is going to be L. Then the difference between L minus L naught we call delta, right? So we define normal strain is going to be delta over L naught. That is we define in mechanics of material or strength of material. So this is stress displacement, strain displacement relation. However, this is the average. Okay. In other words, saying that strain is going to be same throughout the whole member, and then that's going to be the case. Now, going back to the problem like the one we talk about, if I have a hole, right, and apply the load here, then if I look at the strain at that point and strain at that point or strain at that point, they are not going to be the same, like a stress. Okay, so you are going to have a different strain. That means this expression is not going to be true anymore. So you have to define strain at each individual location, not the average value, like a stress. So we have to define that. That's what we are talking about in here, the relation between strain and displacement. So how we derive that one? Let's look at 2D problem. Okay, 2D is easy to draw. So you have XY coordinate system, our reference coordinate system, and I have this delta x or dx or dy. Okay, infinitesimal length of this is going to be 90 degrees. All right. Initially, this motion in the horizontal direction, this is u, and this is v. Okay, the motion of that point. So let's say this point O. Let's say forget about u over here. Let's say this is going to be O, A, and B. Okay, this is before any deformation. So forget about this one. Sorry about that. So O, A, B. Now, this line move because of the external loading. Of course, I exaggerate. In actual case, it's going to be very small. You cannot see with naked eyes, but let's exaggerate so that it moved like this. Okay, exaggerate. Everything is exaggerate. So this point O becomes O prime, and A becomes A prime, and B become B prime. Okay, so there is some kind of change of motion because of that applied load. All right, then this displacement from here to here, okay, from here to here, this x displacement is called u, and y displacement we call v. Okay, u is going to be displacement along the x direction, v is going to be a displacement along the y direction. Got it? Then what about from A to A prime? This is from O to O prime. What about from here to here? What is this motion? This displacement from this point to that point, at least in the horizontal component. That's not going to be equal to U. If this is going to be equal to U, that means what? There's going to be length change. But in general, you expect some change in length because you apply loading. So that's going to be U and what? Again, same concept we apply for equation of equilibrium using Taylor series expansion. So if this point is going to be change is going to be U, then this change is going to be partial du dx dx. Make sense? And of course, you can add higher the term, but again, dx is going to be so small, so you can ignore that component too. Yes.
Can you explain again why we had that du dx, partial u, partial x?
So this is Taylor series expansion. Okay, right? So what that means is that this is going to be the value at x, then value at x plus dx, some nearby value. Dx is going to be some usually small. A nearby value is going to be calculated from this information. Now dx is going to be small, then I can ignore the rest of them because it's going to be higher than the rest of them, right? So this means that if delta is going to be small, then means the value at x is going to be fx, then value at x plus dx is going to be fx plus this component. This comes from Taylor series expansion. So only including the first order term in the series expansion because the, dx is going to be so small. Make sense?
That makes sense. Yeah.
Then what about this motion? This displacement, the vertical, is not going to be equal to v because A is not equal to O. So if this is going to be v, then this is going to be v plus what? dv what? Tell me. dv dy y dy. Because if you look at A, O, and A, this is separate by dx, right? So anything, any variance between the two is going to be because of dx. So in other words, this should be also dx. Make sense? Right? Then let's look at this one. What about this displacement? B to B prime in the y direction. O to O prime y direction is going to be V. Then B to B prime is going to be, again, V plus dV. Again, see what caused the variation? dy, dy. Correct? So the last one. What about this displacement? O to O prime is U horizontal component, so that's going to be horizontal U plus du T. B is separate from O by Ty, right? So this variation should be also Ty. Make sense? So you are looking at the position of the point. So the point relative to your reference point, which is going to be O. So what is the reference that, the distance is going to be Tx. So this have to be Tx and this have to be Ty. Make sense? All right. Then once you understand that one, then epsilon x strain index fraction is by definition O prime A prime minus OA divided by OA, because length change minus original length divided by original length, that's going to be the definition of strain. Okay. Now, OA is more precisely, from Pythagorean theorem, this square plus that square add that square and take a square root. However, this angle, if let's say this angle alpha, if alpha is going to be so small, okay, if alpha is going to be so small, even I exaggerate in here, then means this length is going to be same as change from here to here, correct? Because alpha is going to be so small. Then what is the distance from here to here? How do I calculate that? The distance from here to here is going to be from here to here plus here to here. So that's going to be from here to here minus this one. Do you follow me? So I'm looking for, wish I have another color, but this distance, this thick distance, right? So to find that distance, what I do, from here to here, from here to here, minus here to here, correct? So from here to here is going to be this plus this, correct? And minus U is going to be this distance. Do you follow me? So if you do that, from here to here is going to be dx plus U du dx dx, right? That's from here to here, and minus U. So that's going to be this distance, correct? Do you follow me? Minus OA. OA is going to be dx dx, right? So if you simplify this, U cancel out, and dx cancel out here, and now dx cancel out. What do you get? du dx. Right? What does it mean? Conceptually, small distance, infinitesimal dx is going to be infinitesimal distance, and then the change of the that distance du is going to be the strain at that location. All right, du dx. So that is going to be here. Make sense? Any question for this? Then what about epsilon y? Epsilon y, same thing. If you say this angle beta is going to be so small, I mean, by definition, this is going to be O prime B prime minus OB divided by OB. Okay. And now if beta is such small angle, then this length is going to be equal to this length. Okay. And to find this length, how do you find that length? From here to here minus this one. And from here to here is going to be this plus that. Okay. So that's going to be O here to here, dy plus this component. So dy plus v plus dv dy dy and minus v. That's going to be this distance and minus OB is going to be dy and dy. So likewise here, dy cancel out, dy minus dy, and v minus v cancel out, and dy you can divide each other. So that is going to be dv dy. So again, small length in the y direction and the corresponding change in displacement, that's going to be epsilon y. Make sense? This one, let me show you this one. Epsilon x is in 1D, let's look at 1D, du dx, okay? 1D, only we have a x component. Then du is going to be epsilon x dx, right? Right? Now, if you take the integral from 0 to L along the length of the member, and epsilon x is going to be constant, okay? Strain is constant, what do you get? This is going to be u, right? Delta u, integral is going to be u, and that's going to be epsilon x 0 to L dx. Now this 1 dx, more exactly. So this is going to be equal to L, so epsilon x L. So what this one give you? Epsilon x is going to be u over L. U is going to be equal to delta in our notation. This is equal to delta over L, same notation. Okay. So that's what talk about in the average sense. So everything is going to be constant. Then you got the expression we got from mechanics of material, right? But not always, because strain may not be constant throughout the whole length of the member. So that's going to be more precise every location. Same thing in here. Got it? Now, the last one, the shear. So the normal strain are the measure of the length change per unit length, right? But the shear component is by definition, okay, change of angle. So from 90 degree to this degree minus, if you say this is going to be, what is the right notation? Alpha, beta, gamma, delta. We have used most of the parameter. So let's say this is the phi. Okay, so that is more exactly pi over 2 minus, because originally this 90 degree, phi. So that's going to be alpha plus beta. All right, so that is the change in shape. That's the definition for shear strain.
Oh, what is that? Letter over the.
This one,
Okay,
phi,
two.
phi is going to be this angle. Angle of A prime, O prime, A prime.
I think she means the pi over 2 for the 90 degrees.
So this 90 degree, originally 90 degree minus, so that change in angle, that's the shear, which is equal to alpha plus beta. Okay. And alpha plus beta, as long as alpha and beta is going to be small quantity, you can say alpha is going to be tangent alpha and beta is going to be tangent beta, right? As long as alpha beta is going to be small quantity. We are talking about very small deformation. Correct? Then, what is tangent alpha? Tangent alpha is going to be this divided by that. Right? This divided by that. What is this? That is going to be v plus dv dx dx. That's from here to here. Minus v. That's going to be this distance, right? Correct? And divide by this. Divide by this is going to be this one. Okay, this one. Like a dx plus u plus du dx dx minus u. Okay, more precisely. However, in here, of course, this one cancel out. And you cancel out. If you look at that, this term is going to be much smaller than this one, right? We call dx times du dx. So this is going to be much smaller than that one. So I can ignore this one compared to that. So that means what? I have cancel out that one. So this is going to be t3 dx. Okay, that's alpha term. And plus tangent beta is going to be same thing. This divided by that. So this component is going to be from here to here minus from here to here. It's going to be from here to here. It's going to be u plus du dy dy minus u. That's going to be this distance. And this distance, same thing as we did, but we can easily say that that's going to be almost equal to ty in the simplification. So that you cancel out, this one cancel out. So dv, tu, ty. So that's what you get in here. Okay, so that's the distortion. So change in angle, shear strain. Make sense? Now, if you do this one for 3D, if you extend this one 3D, you can easily extend that. Epsilon z, the normal strain in the g direction is going to be displacement, let's say that's going to be w in the g direction, and dz, right? u, v, w, x, y, z. So that's the normal strain. Okay. Then what about the shear strain? Epsilon xg and epsilon yz. So epsilon xg, look at this one. xy, u, y, v, x. So in other words, u is going to be x component and v is going to be y component. You can see that cross relationship. So in here, likewise, partial, if you say x, then partial x, u, and partial z plus partial z is going to be w and partial x. Do you follow me? Then let's do one more here. Now this is going to be y and z component, so that's going to be v and w component in terms of displacement. So partial v, then derivative is going to be respect to z component. plus partial W, then derivative is gonna be Y component. So that's gonna be the shear strain in 3D. Okay? Any question? So now, once you have this kinematic equation, then let's count that how many equations we have. So kinematic equation is going to be basically three equations, this, and that. So from in 2D case, so from previous, I have two equation, three equation, three equation. So total, how many equation? 2 plus 3 plus 3, 2, 3, 3, 8 equation, right? 8 equation. Then how many unknown variable? 3 stresses, 3 strain, so 3, 3, and how many additional unknown? 2 displacement, U and V. So 3 plus 3 plus 2, 8. So in other words, in 2D theory velocity, you have 8 equation and 8 unknown. And those equation also has some derivative, partial differential equation and also derivative. So it's not a simple problem. Okay. So bottom line is that unless problem is very simple, geometry wise and also boundary condition wise, you cannot get an analytical solution. That's why people develop strength of material, easy to solve. Okay. And so this one, zero velocity, mostly, I mean, even there are some limited solution, okay, actually about this sick of book having all those solutions for zero velocity, but mostly the more realistic problem you have to solve using computer program. So the finite element solution technique has been very successful to solve this kind of problem. Okay. Now, if you go to 3D problem, just to double check, then we had 3 equation of equilibrium and 6 constitutive equation, 9, and then 6 kinematic equation. So 3 plus 6 plus 6, 15. So you have 15 equation. Okay. And how many unknown? 6 strain, 6 stress, and 3 displacement. So total 15. So in other words, you have to solve 15 equation for 15 unknown. That's the standard 3D zero velocity. That's not easy, right? Any questions so far? So in mathematics, I don't know, our human being, our brain or the way we train, we usually have more difficulty solving multiple differential equations simultaneously. Right? So what people try to do, of course, this has some limited success. Not every problem can be done that way. What they try to do was that they try to reduce the number of equations. Right? Instead of that 8, for example, 2D problem equation, solving 8 equations is going to be difficult. So they want to reduce number of equations. So what they do, they want to combine those. And as you combine an elimination process and introducing new variable, what ends up is going to be in some simple case, you have a single equation, especially for 2D, but the differential equations could become higher and higher because as you substitution of that then become higher and higher. So you have fourth order differential equation for 2D problem. Okay, fourth order partial differential equation for 2D. 3D, nobody has successful in doing that so far. So then people could get some analytical solution. So at least people are good solving single equation through some way of the technique. But they are going to solve multiple equations, simultaneous equation for differential equation wasn't that easy. Okay, but anyhow, we are going to solve this one using finite solution technique, so you don't have to worry about that portion. So bottom line is going to be, it's very complex problem if you want to solve that analytically, but numerically solving this one doesn't make any difference. We can apply same concept we learned in previous chapter to here. So far so good? Any question? All right, then those are so-called governing equation. Okay, the differential equation and governing equation. Then any equation, if you want to solve it and then find the unique solution, we have to have boundary condition, right? You have to apply boundary condition. Same thing in your the project. You apply boundary condition. Otherwise, your solution is not going to be unique. So you have to apply boundary condition. Then there are two types of boundary condition in here. In zero elasticity, one is displacement. Displacement in the x, y direction are given. Some constraint in the x and y direction, then that's the so-called displacement geometric boundary condition or essential boundary condition. And they call also geometric boundary condition. Okay, geometric or essential boundary condition. And the other condition is going to be the traction, like this, the temperature, and that's the flux. If you have some, similarity between the heat transfer problem. So traction is going to be a flux boundary condition. So traction are given. That's going to be natural or what do you call? This is going to be geometric, and this is going to be what's the name? I forgot. The natural. I just forgot that, so I'll let you know. So anyhow, this is going to be, the natural type boundary condition. So you have a two type of boundary condition. And also in here, if you don't have geometric boundary condition at all in the problem, then especially static problem, you are going to have singularity in your matrix. So you cannot invert the matrix. So you have to have a proper displacement boundary condition to avoid any rigid body motion. So in other words, if you look at a body, let's say I have a 2D body and I constrain this. So this means here u equals 0 and v equals 0. Okay, at that point. Then I apply load like that. Then what you are going to expect? Even you have this constraint here, you may have rigid body rotation, correct? This body could rotate either this way or that way. So in other words, you did not fully constrain rigid body motion, correct? So at least you have to constrain one more point for either x or y direction. Then you have full constraint from the rigid body motion. If you don't do that, then your matrix equation becomes singular, so you don't get the solution. Right? Transient problem is different because transient problem, we are following solution as function of time. So yes, we are going to see rigid body motion, as well as deformation, then we are going to follow that as function of time. So still we can solve the problem, but boundary value problem, static problem, if you have rigid body motion, you cannot find the solution from your matrix. Okay. So displacement, you have U and V. Temperature, you have only one value at given point. But displacement in 2D, you have U, V. And if this 3D, U, V, W. So you have either one-dimensional problem, of course, only U. So 1, 2, or 3 displacement, depending on the nature of the problem. So you have to prescribe that properly. Now, the traction like the flux, but again, the difference between heat transfer and this solid mechanics, the property in heat transfer, like a temperature or flux, those are scalar quantity. So in other words, there's no, property in direction, temperature. It doesn't have difference in X direction, Y direction like that. As well as flux, is one flux, it doesn't have any component X, Y, Z direction. Flux is going to be always normal to the surface. Okay, that's the fact. But displacement, as I said, at given point, you could have displacement X direction, Y direction, and Z direction. So this is a vector quantity, not scalar, X, Y, Z component, right? Same thing, traction is not a scalar quantity. You have a traction in X, Y, and Z direction, or different. You cannot mix traction in X direction, Y direction together. No, you cannot do that. So if you remember in flux boundary condition, let's say I have a boundary like this, an element. So I have a flux, let's say this is 10, and I have a flux, this is going to be 100. Then at this point, the flux is going to be added from this side and from that side, so added together, because this is a scalar quantity. All right? But in solid mechanics, instead of flux, here, I apply, the traction here, sigma X traction is going to be 10, and it's going to be 100 this way. Then at that point, I cannot add whatever value coming from here, add that together because they have different direction. Okay, so this one is going to produce traction this direction. This is going to produce traction in that direction. You never add them together. Okay, because there are two different quantities. So there's the difference between vector quantity and scalar quantity. So heat transfer is going to be all scalar, but solid mechanics, zero velocity, those are going to be a vector quantity. Okay, so you cannot add X component to Y component as well as Z component. They have to take that as a separate quantity. So here you have traction in X direction. We use the phi, capital Phi, and traction in Y direction. Okay, so if that is given, then we have to have known value. Unknown, we don't have to worry about it because that's we can do anything about that. The known value. Then what is the relation between traction and the stress, sigma X, sigma Y, sigma Z? So that's what I'm going to show you in here. So if I have a domain here, and let's say I'm looking for this boundary, right? This boundary, then let's exaggerate, that's the boundary. Then let's say I'm going to make this one wedges like that on. So the normal vector n, and this is going to be angle theta, then this is angle theta too, right? Then normal vector, especially unit normal vector, this one has cosine theta in the x direction and sine theta in the y component of the normal vector. Okay, and the traction, since we use XY coordinate system, XY again as usual, horizontal X, vertical Y. So let's say this is traction Px, and that's the traction Py, okay, on the surface. And here, normal stress is sigma X, normal stress sigma Y. We assume positive based on our sign convention, tension. And then shear stress, this is going to be, again, assume positive direction, that's going to be tau sub xy, okay? Then, looking at these small wedges, this is going to be very small wedges, but we know that if the body is in equilibrium, then any small piece should be in equilibrium. That's what you learned from statics. The whole thing is in equilibrium, then any small piece of the body should be in equilibrium. So in other words, this wedge should be in equilibrium too. So if you do summation of force in the x direction, then what do you get? Traction is like a stress. That's going to be the force per unit area. So multiply by this area. Let's say this area is going to be L. L is arbitrary, so just denote by L. Then Px times L. That's going to be the stress times L, so that's the force of that one. And which one has horizontal component? Sigma x. So sigma x times, what is this area? This area is going to be L times cosine theta and opposite direction, so minus sign, correct? And which one also has horizontal component? This one. Tau sub xy. What is this component? That's going to be L times area sine theta, assuming unit depth, normal to the paper, and that's going to be also negative, so equals 0. So L cancel out. As I said, those are arbitrary. So piece of x is going to be sigma x cosine theta plus tau sub xy sine theta, right? And if I call nominally this nx and y, so in other words, x component, y component normal vector, then this is going to be sigma x and x plus tau sub xy and y. That's what you get in here, right? Then if I do one more thing, summation of force in the vertical direction, then likewise, piece of y times L, that's going to be the traction in the vertical direction force, and sigma y times, this is going to be L sine theta, right? And this one minus tau sub xy, this component, and L cosine theta. So L cancel out, and phi of x is, now let's put this one first, tau sub xy cosine theta plus sigma y sine theta. Likewise, tau sub xy, this is n of x, and sigma y, n of y. So that is shown in here too. Okay, so traction is expressed in terms of stress, x, sigma y, and tau sub xy component. And then whether this is given or not given depends on boundary condition. That's going to be the traction boundary condition. Got it? Then we have all set of equation and information. In other words, we have a complete set of governing equation and then proper set of boundary condition. And we should be able to solve that problem using finite element solution technique. Got it? So this is some kind of simple review of theory of elasticity. Since you haven't taken any class in theory of elasticity, I spent some extra, time to explain that. But the bottom line is that now you got an equation and boundary condition, and how do we solve that using the finite element solution technique? So, this part is going to be our focus because zero elasticity is not our, main focus in here, but we are going to focus on how to solve that problem using the finite solution procedure. So again, we are going to continue this one next week after our long week holiday. But bottom line is going to be, we are going to apply same procedure, method, weight, residual. So what I said in the beginning, chapter 2, the method, weight, residual, we are going to apply that every single example. Of course, theory of elasticity, if you look at other textbook, then they use different derivation, which is actually a little more simpler for strength of, theory of elasticity using energy principle. Okay, energy principle is going to be easier to drive. However, assuming we are not an expert in structural mechanics, so we are going to apply the same mathematical base of method, weight, residual. Okay, so we are going to develop the formulation from next week, and then we'll continue from there. Okay, any question up to this point? All right, then I'm going to stop recording here.